Hi, and welcome back to the YouTube video lecture series. This lecture is on Chapter 2, Section 5. It's really just about molecules and ions, so it's a little bit shorter than some of the rest. If you remember from the last video and from the earlier sections in Chapter 2, our understanding of the atom after Rutherford's gold foil experiment was that in an atom there was a very dense nucleus right in the middle that contained all of the protons and neutrons, so all of the mass, almost all of the mass of the atom, and then there's a lot of empty space where the electrons were free to move about. So that's our current understanding of the atom. But one thing that we now are learning is that in nature, atoms are rarely found in isolation, just as a single atom. The only exception to that is the noble gases for the most part. So most matter is in the form of molecules or ions. And let's get a couple of definitions out there. And throughout this lecture, I've bolded the really, really important words that you definitely need to know. So keep an eye out for those. A molecule is composed of atoms that are held together by covalent bonds in a definite structure. They can be the same or different types of atoms. Some examples, and in these examples, the way we write this is the chemical symbol for the element. H is the symbol for hydrogen, and these subscripts represent how many atoms there are in the molecule. So H2 represents a molecule that is just two atoms of hydrogen bonded together. H2O, which you've definitely heard of as the formula for water, we've got one oxygen and two hydrogens in a definite structure. And of course you probably know that these are not really what the molecules look like. These are models, and there's kind of a different way to portray them. This is called a ball and stick model for obvious reasons. And then this is a somewhat more realistic model showing the space that the various atoms are kind of taking up. These are some more complicated, bigger molecules. This one here is fructose, and this is the chemical formula for fructose. There's 6 carbons, 12 hydrogens, and 6 oxygens. So we can kind of start classifying these into different types of molecules. A diatomic molecule is one with 2 hydrogens, two atoms, like the hydrogen molecule. And a polyatomic molecule has more than 2 atoms in it. So that would be the case for any of these. An ion is an atom or a group of atoms that carry an overall positive or negative charge. And this charge is the result of the transfer of electrons. Most textbooks use the term loss or gain. I prefer to think of it as a transfer because the electrons can't just disappear into nowhere or be snatched out of thin air. They're always going to and from somewhere. Since electrons have a negative charge to them, as we learned in this chapter, gaining electrons results in an overall negative charge, and these we call anions. Losing the negative charge makes the overall group or atom positive. So we call these positive charged ions cations. The way I've always remembered it is the T in the word cation looks like a plus sign. And ions can also be classified into how many atoms they're composed of. Ions can be monatomic, so just a single atom, or polyatomic, containing more than one atom. Another way to remember that cations are positive is that they're actually positive. Comparing atoms and ions, and let's talk about how we get from one to the other. Here we have a sodium atom right here, and in the atomic form, an atom has the same number of protons and electrons. Sodium always has 11 protons. That cannot change. If an atom of sodium were to not have 11 protons, it would no longer be sodium. And the number 11 we can find on the periodic table. 11 is sodium's atomic number, so that's how we know that sodium has 11 protons. And yeah, when it's an atom, the number of protons and electrons are equal, and there's a neutral charge. But when sodium becomes an ion, it loses one of those electrons and becomes sodium plus 1. So yeah, we've gone from 11 to 10 electrons, and since we've got one more positive charge than we have negative charges, it has an overall charge of plus 1. Chlorine, its atomic number is 17, so that means it has 17 protons. When it's just neutral chlorine, it's got 17 electrons. But chlorine has a tendency to gain 1 electron, and so the ion, the monatomic anion chloride, has 18 electrons. So yeah, you can always kind of check the math here. 17 positive charges minus 18 negative charges, or just minus 18, they offset each other to be an overall charge of minus 1. So that's why the chloride ion has a charge of minus 1. And one convention is that we write that charge as a superscript on the ion. Now, if we have elements that gain or lose more than 1 electron, we end up with charges that are more or less than 1. So iron is an element that tends to lose 2 or 3 electrons. And so it's got 26 protons. If it loses 3 electrons, it's then got a difference, 26 positives, 23 negatives. Then it's got an overall charge of plus 3. Oxygen, it has 8 protons, 8 electrons in the atomic state, but when it gains those 2 electrons, all of a sudden we have 8 positives, 10 negatives. That means an overall charge of minus 2. So again, we write those overall charges as superscripts. And for the anions, for monatomic anions, we name these things differently. So this atom form of oxygen we just call oxygen. But when it gains those electrons and ends up with a negative charge to it, then we drop the ending and add the ending IDE. That goes for all of these anions. Oxygen becomes oxide, chlorine becomes chloride, other ones, fluorine becomes fluoride, which you've probably heard of. It's in your toothpaste most likely. Even nitrogen becomes nitride. So with all of those anions, the ending changes in the ion form. Let's take a look at this in terms of the periodic table. In your video that you were asked to watch on the tour of the periodic table, you should have gotten out of that there's a kind of staircase line here between the nonmetals on the right and the metals on the left. Really, the definition of metal and nonmetal comes from the fact that the metals tend to lose electrons and become cations, while the nonmetals gain electrons and become anions. Another trend to note on the periodic table is that all of these group 1, let me rewrite this a little bit, all of these group 1 elements form plus 1 ions. All the group 2 form plus 2 ions, and all of the group 17 form minus 1, group 16 minus 2, some minus 3s here, and a minus 4 there. There's a reason for it. We're not quite there yet. We'll talk about it a little bit later on in the course, but just observe that trend right now. Okay, polyatomic ions. As we discussed, these are groups of atoms that have an overall charge, and I like to think of them as charged molecules, just the way that monatomic ions are charged atoms. An example of this is nitrate. Nitrate has the formula NO3 negative, and it's a common ingredient in fertilizer as well as preserved meats like bacon. Don't mean to make you hungry during this lecture, but yeah, you see nitrate is just a preservative, and so it's found in some of those meats. It's also toxic to humans at high doses. Some people argue that you shouldn't eat too much preserved meat. That's kind of the role of nitrate in why preserved meats are considered unhealthy is debatable. There's also a lot of salt and fat, but it's kind of an open debate right now, I would say. It's also a naturally occurring compound or ion, and so it's not totally foreign to the human body. It's there naturally as well. So thinking about polyatomic ions to know is that they tend to stick together. They don't break down very readily in reactions, and they're often preserved in reactions and just switch the other ion that it might be bonded to. So it's important to be able to recognize polyatomic ions, and unfortunately this does involve a lot of memorization. So I'm going to give you guys some time to get there on memorizing polyatomic ions, but to be able to name and identify polyatomic ions is an important skill in chemistry, and we'll use it later on in the course to be able to predict how they react in a reaction. So we'll talk about this list in class tomorrow, Wednesday, but the things I want to point out right now are that there's a number of different kinds of polyatomic ions, and there's kind of different ways to organize them. This particular chart has the cations listed on top. There's not very many polyatomic cations, and the polyatomic anions listed on the bottom. They are broken down by -1 charges, -2 charges, and -3 charges. So we'll talk about some strategies for memorizing them, but I wanted to show them to you at this point, and we will discuss them further in class. So that's it for now. So thanks for watching.